Welcome back. Today is a free build day, so I thought I'd take that as an excuse to kind of go a bit more into some of the science stuff that I'm hoping that I can use Blender to help me with. One of the reasons I'm learning Blender is to learn math and science animation, so take this as kind of like a test of what that would look like. So today we're going to be making a wave, and waves are super important because they basically govern how light propagates or how light fills up a room, how sound can fill up a room. It governs how fluids move. And when we say fluids in physics, we mean gases and liquids. So they're very important. And for me personally, I've been doing a lot of work on something called interferometry. We're basically trying to get really good data from the sun relating to solar flares and coronal mass ejections. But I'll get into a little bit of that later. For now, all we want to do is create a plane. Why do we want to create a plane? Well, we want to basically create a wave out of this plane. And so we're going to need to change the position of a lot of these points. Before we do that, let's size it up just a little bit. Maybe something like that. So to create a plane, or to create waves, first we need to create a more refined mesh. So basically right now, if we went to edit mode, you'd see that this is just, one block. And so we want to use a subdivision surface modifier, and we need it to be, because waves are kind of like smooth, we want it to be pretty refined. So we're going to set both the level viewport and the render to 6. And we're going to change it to simple because instead of a circle, we'd like it as a square, just for now. Once we have that, we want to add another modifier, and this is going to be geometry nodes. We haven't covered geometry nodes yet in class, so I had to kind of like look this part up. So I'm a little bit rusty on exactly how they work, but the general gist is that once we create this geometry node, we can then kind of like do some math to adjust the positions of parts of our object. So when we do this, go to geometry nodes, and we have a group input and a group output. And in between the group input and the group output, we want something that can change our position. And so what we do first is we come and we want to cut this link, and then we want to create in between them something called set position. And the set position will, once we finish setting this up, allow us to adjust different parts of our plane at different points in space. And so to do that, we need an input. So our input is going to be the current position. So it's going to read in the position of every single point in our plane, and then it's going to do some math with it. And before we get into the math and setting that up, I created a little Desmos presentation. So I'm going to use this to kind of explain the underlying physics before we see it implemented. So you see here that we have a sine wave, which is the same as, just a general wave. And we want to recreate this, but in 3 dimensions. But to understand something in 3 dimensions first, it helps to understand it in 2 dimensions. So what you see up here is the equation of a wave that you might learn in a typical physics class. So you have A, which is a constant, times the sine of, this is related to position, kx, and wt is related to time, and then plus some d value for an extra distance. None of that probably makes a ton of sense to you right now unless you have some background on this, so don't worry about that. We're going to start from the very simplest and try and learn visually, because I find that's the way I learn best. So I mentioned that this is position and this is time. And the reason that we have both position and time in one equation is because think about what we want to measure typically when we're talking about a wave. Or even not typically, just specifically in our case. We want a position, right? We want a position, and our position is this y value. And so what having an x and a t value is basically saying is that if we want our value, our z value in our case, even though it says y here, because instead of having just propagating an x, we're propagating an x and y. But that's besides the point. What this is saying is that we're going to have some motion due to x and some motion due to time. And to understand that, let's look at time first. So if we just have our basic equation and we want to move time, let's see what happens when time starts moving. So we're at t is 1, it's going to go up to t is 10. Look at that. You can see it's moving to the right slowly, or not slowly, at a speed, and then when it goes back from 10 to 1, it moves left. So what this is telling us is that as time would normally move on, our wave would move from left to right. Okay, that seems pretty simple, pretty self-explanatory. And now, what goes with this t term? We have a w term. Okay, let's see what happens when we move w. Okay, it also moves left to right. So w is not, in fact, our time term, but it is kind of a modifier to that time term. To understand that, let's first look at position, and then maybe this will make a little more sense. When we say we want the position to be... let me rephrase this. I feel like I'm making this more complicated than it needs to be. Let's look at A and D, and then we'll go back to the middle of the sign, because these are much simpler. If we wanted to move our wave up and down, the entire wave up and down, that is what D is for. So you can see as we move D down, it goes down. If we move it up, it goes up. You can play this animation, you can kind of see it move up and down. Okay. In Blender, we don't care about this because we can physically move our object up and down, or we can do it within an animation or something like that. So we don't care about D. And if you look at this bottom equation, this is what we're going to be creating in Blender. I'm just trying to explain now how we're simplifying the general equation to our Blender equation. So because we can adjust the up and down in Blender, we don't care about it, we get rid of it. Okay, now we have this equation. When I was talking about the time and the time modifier, that can be equated to something called a phase shift. So if we have a point in time or a point in space, let's say this point, and we want to figure out how far away this point is from this point, well, you can look at the x position to say, like, okay, it's this is negative around -1 and this is around 0, so maybe they're 1 away. But that has different amounts of usefulness depending on the wave that you're looking at. For example, some radio waves, like the ones I use in my research, are like hundreds of meters long. They have a wavelength that's hundreds of meters. And all the wavelength is the distance from a peak to a peak, or a trough to a trough. We call the time that it takes to get from one peak to one peak, or one trough to one trough, the period, and it's measured, as you would guess, in time. So sometimes it might take a split second, like at the speed of light. We're traveling super fast, so peak to peak or trough to trough, it might happen millions of times a second. But instead of doing per second, the period is basically saying this is how many seconds it takes. And then we have something called a frequency, which you've probably also heard, which is saying how many times per second do you get peak to peak movement. And what adjusting the k value does, the value that goes with our x, is it adjusts the frequency. So the higher our k goes, you can see as it increases, the peaks get way closer together, and then as it decreases, they get further apart. And then they flip over as k becomes negative. But you can kind of get the idea that if we wanted a super condensed wave, we would want a high frequency. If we wanted a lower frequency, if we wanted a more spread apart wave, we'd want a lower one. And I said frequency, that's incorrect. K is actually something called the wave number, which is related to the frequency, but also has a dependence on 2 pi. That's kind of out of the scope of what I want to talk about today. But yeah, for those who are more inclined, you might, more physics savvy, you may have pointed that out. Okay, now we have all of these, and we've replaced WT with our phase, and we've gotten rid of the D because we can adjust that manually. So all we have now is we have our Y value, which is what we want. This is our desired position. We have our our X value, which is our current position that's being read in. And in our case in Blender, this Y is a Z, and this X is both X and Y. It's just the distance in a circular direction from the point that we're at. It'll be a lot more clear once I actually make it, so let's move on to that right now. We have our position, and what do we want to do with our position? We want to feed it into a distance modifier. And what this distance does is it basically takes our first location, so the 0 point, which is the origin of the wave, and it says from the position we're reading in to 0, 0, how far apart is that? So if you're at 0, 0, this distance will be 0. If you're 1 unit away, it'll be 1. If you're, let's say, 3 units in this direction and then 4 units in that direction, well, then you have to do some trigonometry. But if you remember your basic trig, there's a 3, 4, 5 triangle. So there's stuff like that. But instead of having to do the math, it does it all for us, which is very nice because math is a little difficult sometimes. from this distance modifier, we want to take our value that we've gotten, so how far away we are from the center, and we want to plug that into a multiplier. Why are we multiplying? Because if we go back to the equation that we previously had, what we've basically taken with our distance is just this x value. Remember, it's both x and y, but for our purposes, we can just say it's x, and now we're multiplying it by k, the wave number. So we've multiplied it by k. I'm going to set k to around 10, just because I tested this out earlier, and that seems to work pretty well. Then we want to move this value. And what do we do once we take the value? Well, take a guess. If we have kx that we've now created, what's the next thing we would want to do? Like, look inside the parentheses next to the sine function. What do we want to add here? Well, we want to add some phase shift. And so in order to add a phase shift, the word there that's important is add. So we take this and we add some value. Let's start it at 0 for now, but you'll see how that can come into effect. With all this, let's also kind of shift this over and move this guy out here just so we have a little more room, because it does get quite large. Once we've added that value, let's go back to here. Okay, we now have everything inside the parentheses. So if you've ever remembered PEMDAS, we're kind of doing the same thing here. We've taken the x, okay, then multiplication comes before addition. So we do the multiplication, then we do the addition, and now we finish everything in the parentheses. The function that adjusts what everything that's in the parentheses is a sine function. So we now need to feed all of this into a sine function. So we can do that. We just type in sine, and it comes out here. And then once we have the sine function, what comes outside of this? So once we have everything that's highlighted here, we now want to multiply it by this a value, the a value that, remember, scales up and down the amplitude of the entire wave. So we add a multiply. Okay, and you might be thinking, okay, we're probably done now. And the value that I found that works decently is 0.1. You might be thinking, okay, can we just feed this multiplied value now into the offset? So let's see what happens if we do that. And you see it kind of looks weird. It's like, why is this happening? It doesn't look like it's propagating equally in every direction. There's kind of like this direction is going that way, and this direction it's kind of coming out. Like, it doesn't look like a real wave. And the fix to this is actually pretty simple. Let's undo this connection. How do we do that? Oh, couplings, yeah. Okay. So what we can do is just add in a combine XYZ value. And oops, it's not supposed to be in X. Instead of X, we want it going into Z. Because remember, everything that we've calculated here is telling us the Z position of every point in space based off of that point in space. So now we have all of this. This is finally enough that if we plug this into offset, look at that. We now have a 3-dimensional wave. And that wave is the same, it's the same underlying math, I hope you can see now, that we're using here. So let's to kind of review. If we wanted to adjust the amplitude of the wave in Desmos, we adjust this A value. That A value was the last value we made, remember? So that A value is this multiply function. So if we adjust A to move increase, you can see the amplitude goes up. If we go down, amplitude goes down. If it goes negative, it goes up again, but in the opposite direction. So 0.1 was about good. Likewise, okay, we see the sine value. Inside the sine, remember, this is our x value that we got, the distance. And so what goes next to the x is the k. Remember that k in Desmos changes how close together the peaks and troughs are. So you can see as it goes, the higher it goes, the more condensed they get. And then as it gets lower and lower, they get more spread out. The same thing should happen if we adjust this multiply value. So right now it's at 10. If we were to increase it from 10, it should get closer together. And you can see that the peaks and troughs get closer together. And then if it gets further apart, we can see that the wave becomes less spread out until it gets flat. And so I found that 10 gives, you can tell it's a wave if I do that. So I put it at 10. And then lastly, remember we have this phase shift. So the phase shift is WT, but what you can do is I made it a second function which just includes phase, so we can see what happens just when you shift phase. It just moves it left and right. And so you can see that when I move it to positive values, it moves left, and when I move it to negative values, it moves right. In physics, to account for this, we typically say it's kx minus the phase instead of kx plus the phase, so that when you move to a positive value, it goes right and negative is left. But in the case of Blender, it's not super important because it's propagating in every direction. And when we animate it, we can animate it based off of certain properties. I'm not going to be animating it today, but that's a general gist. So you see that it moves left and right, but it keeps the same distance from peak to peak and trough to trough. So do we see the same thing when we change this value? Well, yes. It's just kind of a wave doing its thing. You see as I move to higher and higher values, it kind of looks like it's coming in, which is not typical wave, what a wave would do. You would see typically if, if something was bobbing in the water, the waves would propagate outwards. And so likewise, it would go like this. Okay. Is there a subtract actually? That might be, I didn't even look. I was just kind of following a tutorial when I figured this out. Oh, okay. I think this should work instead. Let me just try this out on the spout. If we get rid of this like that, and then now if this goes up, yeah, perfect. Okay, there you go. So you can see how the math and the Blender setup kind of go along with each other. This can be 0, it doesn't need to be 1, in the sense that we now have all of this. If we wanted to adjust the overall up-down position, what do you think we should do? This is just like a little, I don't know, think of it as like a mini quiz, although you're not getting graded, of course. If we wanted to add this D value back in, hypothetically, instead of actually using Blender, okay? Well, think about how we've set everything up in the past. We kind of did PEMDAS to work from the inside out. So we took our position, then we multiplied, then we subtracted, now we had everything in the parentheses, then we do the function that adjusts what's in the parentheses, then we did the multiplying that adjusts everything like that. And then from this original equation, well, we have this plus D. And that would, if you were to evaluate a math term like this, using PEMDAS, addition and subtraction come last. So this would come last. So if we wanted to add that in, what we could do, if we cut this link, hello, there we go, is we just make a new add function. So this can go in here. Let's just create a little bit more space so we can see, and then we put this into Z, and now you can see that if we adjust this is now our D value, it moves up and down. So isn't that pretty cool, pretty nifty? I think so. I think let's try and get it kind of aligned with, so that the bottom of the wave is aligned with the plane, like where this orange kind of highlighted area is. So to do that, let's look at the general amplitude of our wave. So we see that it's 0.1 here, right, if we moved it up and down. So at 0.1, an amplitude of 0.1 means that the peak goes up to 0.1 and the trough goes down to negative 0.1. So I think, yes, if we put that at 0.1, look at that. We now have it situated so that it exactly lines up with the bottom of the plane. And you can see that it's good because there's these artifacts. It's like just ever so slightly kind of shifting through, but I promise that is how it's supposed to be. So with that, we now have our wave. I guess let's add some color now. Oh, one more thing. You can kind of see how it's still a little pixelated, right? We definitely have a wave shape. Like you can tell it's kind of a liquid, but there's still, these squares that you can see. And so one way to fix that is to add a second subdivision surface modifier and set it to 2, 2. And I found that seems to kind of fix the problem. You can still see there's some squares like right here, but from the top it looks pretty good. So pretty happy with that. Let's add a color. In this case, it's a wave. I'm assuming it's water. Let's make it, watery colors. Am I in the wrong mode? Okay, here we are. I never tried coloring this before, but it seems, what is going on here? Why is it not, okay. I've assigned it, oh, of course. I'm being dumb. Okay, there's our water. Okay, so we have our water now. If we go into shaded mode, you can kind of see that there's shadows based off of this light source. We have our light source here. you can see that there's shadows on the back side opposite where the light source is. So if we wanted to kind of adjust that, you can see that. Let's make our light source a little bigger and maybe increase the power to like 2500. And now if we were to move around, you can see that based off of those peaks and troughs, we get different light, which I think is pretty nifty. If we go back to our camera, I think this is a pretty good angle to kind of see it. So you get the overall gist. I've been working on a duck model. I mean, it's not fully complete yet, but the idea is that if you use a duck in a lake, you can kind of explain interferometry. And so maybe I'll do that in a future Sunday video if we have time. How much time are we in so far? Oh, we're just exactly at 20 minutes. Perfect. So I hope you like that. Let me know if you have any feedback as to the quality of the teaching. Obviously, I'm not a teacher. I'm just an engineer. But I'm hoping that using some of the skills I'm picking up by learning animation, I can kind of convey some of the math and science that is typically a little harder to understand in a way that might be slightly easier to understand, because I always found that visualizing something helped me, so I'm hoping it can help some other people. Anyways, that's all for today. Thanks for watching.